Yeah, probably I want to emphasize several things. First, maybe I should share my windows first. Oh, have some issue with the connection. Yeah, but now it's better. Yeah. So I share the window. So I put something in the study module. So first, I want to emphasize like every time some student ask me about our arrangement of the subjects, I think I emphasize again. All most important thing is in the week one. In the week one, I put some project description and also study guide. Here is in the week one lab, so you can see. Uh, we have study guide here. So study guide is the most important part. We need to see. So this table, you need to keep in mind of this table today. So this week is week 6. So we need to finish assignment 1. So I hope you can all finish tomorrow morning, and we need to prepare for next week. We will have a seminar 1. So in order to help you to prepare the seminar 1, end of today's lab, because I think lab time is very important for all of you. And after today's lab, I will be. Can you hear me? Hello.
Yeah, we can hear.
Oh, that's great. So I think like next week, I mean after 9 o'clock, I will still, me and the tutor will still in the room, maybe for half hour. So that means from 9 to 9:30, we are still in the uh, not face to face, is in the web. We can answer your questions and about the assignment 1, mainly for the seminar 1. So how to prepare. If you have any problem about seminar 1, just ask us. So in the future, maybe if necessary, all after from 9 to 9:30, I mainly answer your questions. I will be in the common room. I will not go the individual room, because previous several times I feel like there's a common questions, and I will try my best to join each room for maybe at least 5 minutes to discuss about the project and the future arrangements. Um, so you can see after next week, so week seminar 1, and then during the student still week, I mean I'm not sure like if necessary I will maybe still use some time to help you about the project, and also mainly for assignment 2. So assignment 2 today I want to emphasize assignment 2. So assignment 2 is really important. So it's mainly we learn the analog circuit design. So it's a very important subject, important assignment. So I will basically give you all the fundamental knowledge and fundamental skills uh, to finish this assignment. So I know some student is from science, with a science background. We especially want to help this kind of student. Like we give them at least the fundamental part, the for the assignment. So if you have any questions, just let me know, and even you can just directly interrupt me during the lecture time. Just let me know. So we focus on the assignment 2. I think start from this week, we are focused on assignment 2. Uh, of course, assignment 1, because the final project, we should also put some time to there. So that's my plan. So in that case, uh, The next part is have you you read my module, right? I put some pre-work. It's been mainly this for this week is for the we already discussed the ECG and the human circulation and heart system, and also we discussed the EEG is for the and also the human nerve system. We have central nerve and the peripheral nerve system, and also we discussed the EEG. So today we discuss another related with nerve system called EMG. It's muscle signal. So EMG is actually is quite useful for uh, rehabilitation. For example, recently we have project is use EMG to develop exoskeleton to help human for the help for the stroke patient to do the rehabilitation. So we have use EMG. So EMG is some project is also use EMG. I remember there's a I think maybe we have some like motor control we use EMG. This is one project. Uh, you can see the pre-work is here. So I put I think this one is not working, but I will change a new one. But here is the some reading material about EMG. So I think EMG before I talk about there when you want to build a EMG recorder, it's very similar with ECG and with and EEG. So, but they have different range. So you need to adjust the amplification, the amplification part. So most other part is very similar. They all have the electrodes like a sensor, but their range is different. So for the EMG, so their range is very quite different. They range from 50 microvolts to up to 30 millivolts. So it's quite really depends uh, where you put. So for the EEG, EEG is a most weak signal. So from 10 to 100 microvolts. So ECG is from 1 to 5 microvolts. So if you know how to design a ECG, so for the assignment 2, we mainly discuss about how to design ECG, but you can use this technique to develop ECG, EMG, and EEG recorder. But to be honest, the most difficult part is EEG because EEG signal is quite weak, but their structure is similar. So maybe we look at the. I remember in the beginning part, I talking about the how to design ECG, right? So first is the instrumentation amplifier with gain of 10. So this part, I think I discussed before. Today maybe I ask Jeffy after our lecture. Jeffy will use multi-sim step by step to tell you how to build instrumentation amplifier. But maybe it's a little bit quick because maybe because we need some time to do the lab. And then it's high pass filter design. And I will discuss with you both high pass and the low pass filter. Maybe we start from low pass filter design. So the amplifier can 100. This is a maybe you can use non-inverting or inverting amplifier, or even use differential amplifier to implement the 101. So this is also easy. So I think after this one, the instrumentation amplifier, and then you know how to design low pass filter, and then I think the overall, if you can fundamentally you can implement the assignment 2. But if some student is very want to have some challenge, so that is a fundamental requirements, basic requirements. But if you want to get bonus marks, maybe you can also they have some optional part. I think I put into the assignment requirements assignment here. So this is assignment we look at assignment 2. So it's mainly is so you maybe need to spend some time to think about the assignment 2 now. So you can see we have low pass and high pass and band pass filter. Uh, some this is a fundamental you need to design, but it's notch filter is optional. So in that case, if you don't have enough time, the notch filter can be in the future. I will introduce you explain why notch filter is not fundamental. So maybe we can use a digital filter to get rid of 50 hertz noise. So we design a digital notch filter, but we low pass we always need this called anti-aliasing filter. So I will explain what's aliasing in today's lecture. So anti-aliasing filter, anti-aliasing filter we always need it. So this is essential. So this three different filter you need to design, but the band stop filter here we can use digital filter to implement. We also have a right leg drive design. This is optional as well. So I put some reading material about right leg protection circuit and also diode protection design is also optional. So it's also data acquisition design. Of course, this is also optional, like means, but in the future, maybe in the future next year, maybe if it's face to face, we normally use Arduino to ask student to implement this part. But for this year, I think it is nearly impossible to do this part. So even though it's optional, maybe no one can do it. So so this is some requirements, and I will discuss about frequency response for low pass filter, how to test this as well. Maybe Jeff, you can discuss about this frequency uh, response, how to use a multi-sim, give a sinusoid, how to see the response of the filter. So basically, for different, like a filter is also a linear system. So if you give a sinusoid, the output must be also a sinusoid. So, but they have same frequency, but the magnitude and the phase will be changed. So we need to based on, for example, they have several frequency. You select frequency one, for example, 1 hertz, 2 hertz, 10 hertz, 100 hertz, and then the input is a different frequency sinusoid, and then you put to your system to see what's the output, what's the gain, and what's the phase. So you can draw this fill this table and draw a figure, so you can see the response, frequency response, both low pass and high pass. So and also CMR, you can see assignment 2 is, if you just like basic requirement, is very easy. It's just like a 2 filter and 2 amplifier. One instrumentation, one is the instrumentation amplifier, another is a normal amplifier. So you have 2 amplifier, 2 filter, and then you need to test what's the CMR for your uh, for your instrumentation amplifier. So and then a conclusion, and then but the things is we need to have BOM list. So you need to list all your the component you use. So this is assignment 2. You need to print it out and have a good reading, and then think about, because week 9 will do week 9. So this one I hope you can learn some basic knowledge about analog filter, analog circuit design. This general name is called analog signal signal conditioning. Now we look at back again to the module. Today I'm not sure how many students uh, see the pre-work. So the pre-work I put some very important thing. Actually, one is you can see I put one is active filter design. This is theory about how to design a filter. Another is uh, how to design a filter use multi-sim. So this one, I think I hope like most of you read this one because this is a pre-work. This is very important. You can see this one. This one not give you any voice, but they show you step by step how to design the low pass filter, how to implement low pass filter. So they first put op-amp. Yeah. Actually, you can search in the Google, in the YouTube. You have some other, and also you can help from the multi-sim. But I'm very sorry, like apologize, like we push the IT people to install uh, multi-sim in the workspace, but unfortunately they still haven't installed yet. So but we push from next week until today. They said they will install quite soon. Because I know that some students only use Mac computer. Using Mac computer is very difficult to install uh, the multi-sim. So I think if you have the Windows system, that will be easier to install the 6 months free multi-sim. So this one I leave to you because we are very time is very short, so we cannot uh, spend too much time here. So we look at another one is more important than this one. So
is going to vary with frequency.
So during the early student feedback survey, some students said like if we put some video there, we should explain in detail. I'm not sure that's a good idea or not. I just want to ask you, what's your opinion? Should I discuss about the video, or should I just like I have the PowerPoint? I just based on PowerPoint to display because for the video, I think I give you to watch after class. I'm not sure what's your opinion. Do we should focus on the video or some of the videos? Oh, I mean because the previous year some students said like you shouldn't spend too much time for the video because video they can watch after class. So I'm a little confused. But now I mean I still emphasize some important part of the video, and I just say which part you should read, and then you go home to read. For today, at least for today. But if you really still want me to watch some maybe some whole video, I think I still can change, but I think from my understanding, I think the most important is we select some part. So for this one, you can see it's a
The
video for.
calculation is 1 over. Characteristics that we can see in a single stage device and how we can improve.
So you can see this is the low pass filter, right? So this is the pass band. You can see the pass band. This is the cutoff frequency. Cutoff frequency, like this is approximated body plot, then frequency response. So if it's a real frequency response, they always have a -3 dB drop. This part is called cutoff frequency. So in that case, for this uh, circuit, they build a circuit. It's a cutoff frequency is 1 radius per second. So it's not 1 Hertz, 1 radius per second. So this one is he want to design this kind of filter. You see this video, they will show you how to design. They they compared with the passive filter and active filter because for this assignment 2, we mainly ask you to design active filter. So you need to know what's the advantage of active filter. So active filter have several advantage. So
On
here,
this, how an active device compares to a passive device, a two-stage Sallen key filter with feedback resistors to set the dampening factor, and a two-stage without resistors, and this time we have to use the capacitors to set the damping factor. And we'll talk about how to make multiple stage filters and how to set the resistors or select the resistors to get the proper damping factor to get the characteristics we're looking for. So let's go ahead and
so that's mainly the video show you. So I think this is a very good video. So, we have even better idea is like if you don't know how to design the filter, we give you a software. So you can use MATLAB. You download active filter design, and also you have lots of other filter design software online. Sometimes it's on some software is online software. You can directly tell. You just tell what kind of filter you want to design. For example, low pass or high pass, and you tell them what kind of cutoff frequency you want, and then they can directly design the filter for you, and they give you the capacitor value and the resistor value. Because this semester we are not ask you to purchase the resistor and the capacitor, so you will no need to go to JECA, but the previous semester student must go to JECA purchase this component, and they learn a lot because they know what kind of resistor and capacitor they need. For example, some resistor value, for example, you select 10 macro 10 macro farad. That's actually if you because for the filter we design actually is the anti-aliasing filter. This filter should be using non-polarized capacitor. And for the non-polarized capacitor, if it's a two, for example, 2 or 4 microfarads, that will be quite big. When you go to the JECA and you will look at, oh, so big, and you cannot use it, cannot put in the circuit. So you need to use a small value capacitor because when you change the key parameters, for example, cutoff frequency of a filter, you can either change resistor value or change the capacitor value. So you need to balance. You cannot select a very small resistor value, use very big capacitor. And the big capacitor, number one, the size will be very big. Number two, they will have some other side effects. So you need to balance between resistor value. You also cannot use a very big resistor value. For example, if over 1 mega ohm, that will too big. For the capacitor, you cannot use, for example, over 2 microfarad. So you need to be less than one. Should be less than 1 micro. Less than 1 microfarad. So you need to be careful. So that's for this semester, like because we not ask you to build, but you need to have some knowledge about that. By select, you maybe go to the website to check the size of the capacitor value and the resistor value. For example, here you look at this one, is a filter. Like this is a very simple. This is high pass or low pass. Is anyone can see this is high pass or low pass? So this is a low pass filter, right? Can you hear me? Hello?
Yeah, we can hear you.
Oh, that's great. So
Yes.
yeah, so this is a low pass filter, right? Why this is a low pass filter? Can you derive the transfer function of this one or this one?
No.
Maybe I give you a quick derivative about why is this low pass? Because you can see this one. What's this circuit looks like? So this is a amplifier, right? So in the right hand side with the op amp, we just teach you how to analyze, you remember we have three type of amplifier. One is a non-inverting amplifier, one is inverting amplifier, and also differential amplifier. What's the name of this amplifier? This non-inverting amplifier, right? So in that case, you can tune the gain for the this passive filter. If this passive filter, you cannot change the gain, right? You cannot change it. For the active filter, you can change the gain by changing the parameter, the resistor value. Do you still remember how to calculate the gain of this one? So it's 1 plus R2, RF over R1, right? So you can get the gain. And also this one have other very good property for if you use active filter. So we will show you how to implement active filter, because they also teach this video also teach you what's some very particularly important circuit called silent key filter. So for example, second order silent key filter, and things very important. So I hope you can read this video carefully. So maybe we continue a little
and get started.
So this is really based on your knowledge, previous knowledge. If you are from, for example, if you never touch about this kind of concept, stop band and things, probably you need to watch whole video.
Few parts that we have to deal with, very few components. However, there's no amplification in the circuit, so the best we can hope for in a perfect world would be if we had 1 volt in at, let's say, 1 hertz. That's going to make XC practically infinite. We would hope to have whatever load is hooked up out here still have 1 volt here. Obviously, we can't get any more. So
we're supposed to.
You cannot hear the voice?
No.
Okay. In that case, I will not watch this video. Maybe I first derive the maybe I use I think not use this video to pull it too much, but I put this one for you. You can know what's the advantage of use active filter. So active filter have lots of advantage. So you can see this is the gain, right? I mentioned about this gain. You can change the gain of the filter easily, and also they have a decoupling, reduce the decoupling, and they no need to use the inductor, so they can they can also isolate things, so they can. But the disadvantage, they need power supply, right? So this is they analyze the frequency response. So they're talking about different kind of filter name, but you don't worry about this one. Butterworth, Basel, and Chebyshev, and elliptic. So this is a kind of they can all implement the filter, but they have different name. So this is a silent key. So you can see this is a second order because we have two memory elements. So C1 capacitor have memory, so they are when you charge a capacitor is related with your previous voltage as well. It's not current, but for resistor value, they don't have memory. So that means they have two memory elements. They at most is a second order system. So in that case, it's second order filter. So they have lots of they did lots of analysis how to implement. So this one I will show, you can see you can cascade. For example, if you want to design 6 order Butterworth filter, you can just simply use 3 second order filter, merge them together, serial serially connect them together, and then they can construct a 6-order filter, and they can design independently design each part, because you use the active component. The input gain is big enough, so they can tolerate the disturbance, the coupling. So in that case, that's a good thing. And even better, we will teach you how. This is teach you how to use hand to select the ratio and the things, and also you select how to select the value. I will teach you how to use MATLAB to directly implement, to calculate the value. So you only need to check after you design. You put into the multi-sim, and then you use the oscilloscope, and use function generator. You generate a sinusoid, and to test whether your design is low pass or high pass, is what you want. So this is the procedure. So I will use this one is also teach you how to implement, but unfortunately this semester you cannot do it. But here they give you some even some how to use a real oscilloscope, the things they give you very detailed explanation. So I believe if you can totally understand this video, and you can halfly see that you can design a filter, right? And then you need to some hands-on skill in the future. But now you learn mainly use multi-sim to learn this skill. So now I go. This is very traditional people to design a filter, but now because we can use the web, use software to design. So here I go. This is the part I put in the preparation part. I hope you have already read this part, because last week we already finished the filter. I mean the multiple. I mean the amplifier design. We emphasize non-inverting, inverting, and the differential amplifier. And then based on this knowledge, you can analyze the filter as well. So the filter design is based on the amplification and the RC circuit. So we look at the next part. You can see I put some video. This is the EMG and the motor unit. So you can read what's EMG and things. If you, especially when you do some project with EMG related. So next week, why we need the seminar is actually the project for this subject. We want to every student learn lots of instrument, but it is not possible. So in that case, we give a seminar. You can learn other people's project, and you can learn some relevant biomedical instrument. So that's our purpose. So in that case, some group they study about EMG. So if you never touch EMG, you can learn from other group. So here I put some video you can read, but here is the filtering part I want to emphasize. So maybe I still go to so this is a filter design. Maybe I use so this is a very, very important part, and I also want to use MATLAB to show you how to design the filter. So today I want you concentrate for this one, and later Jeffy will show you how to use multi-sim again, and also maybe he will teach you how to build a instrumentation amplifier step by step. But later we will teach you how to implement the filter. So this is a filter design. Actually, what's a filter? Filter actually is just like, for example, this is the unfiltered signal, right? They have high frequency noise. After you use low pass filter, you can get rid of high frequency noise. And this is a frequency based filter. In the future, you have some other filter, like maybe you heard about Kalman filter. This kind of filter is based on the probability analysis. So this is a different kind of filter. but the most commonly used filter is still frequency based. And also we can classify as filter as analog filter and digital filter. So digital filter is very powerful, but sometimes it's very easy to implement. That's why most of the time, if you can use digital filter, you will not use analog filter. But sometimes you never, you cannot get rid of, you still need to design analog filter. So for example, we design EEG, ECG, EMG, this kind of signal, this analog signal, we need to use analog filter to do the filtering first, and then we can in the future use digital filter. So today I will, this subjects will not discuss digital filter design, but in the future, if you learn biomedical signal processing, that subject will emphasize for digital filter design. So for this one, analog filter, we have a element based classification. We have active filter and passive filter. So this is whether you use op-amp, this you need power supply. If you use op-amp and the power supply is an active filter, and others without power supply is passive filter, they have a disadvantage and advantage. So this one is depends. For the frequency based, we have a low pass, band pass, and all pass, and we also have a high pass and band reject filter. So for this ECG design, actually we need this fundamental requirements is a low pass, band pass, and high pass. So band reject is optional, and all pass. All pass sometimes is very useful as well. You maybe heard about what's that called Hilbert filter, Hilbert transfer, and also for the filter, like we mainly have a ideal filter and actually or non-distortion filter, but actually ideal filter is only is not possible in the real case. But we want to some property. First, we want to the constant gain. So there's no ripple. So for example, here is no ripple. It's like pass band is very flat, and also the roll-off is very sharp. So that means here is not good because it's gradually stop to go to stop band. So we want to ideal one. We want to sharply go down here and stop. So this is not possible in the real case. And we also don't want to any phase change. So if you have a phase change, and then you will have also influence some distortion as well. So if you can, because any system, dynamic system, have phase lag. If you cannot avoid phase lag, if your phase lag can be linearly with the frequency, that also desired. So for the continuous filter, we never can implement this, but for the digital filter, we can implement linear phase. So this is a very brief introduction about filter design, and we look at a very simple passive. This is passive low pass filter. For this one, because this one, why is low pass? Can you derive the transfer function? Maybe I quickly derive the transfer function. Why this is low pass? I maybe use this. So we did a low pass filter. So it's something like this. If you have a so this is input. We use UI. And if it's this is a resistor value, this is not a power supply. This is a resistor. So we see. So this is the U out. So this output. So for this one, why this is low pass? Intuitively, you can think about like this, because if this one is a high frequency, if this frequency very high, right, sinusoid, very high frequency, and then because the capacitor you can treat as if a high frequency means they connected, because they can sensitive the change for the capacitor. So in that case, the voltage between of the output of voltage will be very small, because your resistance is very small. So you normally this one your output is also small. So this is a high frequency will disappear. So if you measure here. On the other hand, if this is a low frequency, if this one change very slow, and then you will see the limit case is if this is DC, if it's DC, right? And then actually the voltage UI is equal to the UO. That means like if there's no current here, finally no current here, so the voltage in the capacitor is exactly same with the power supply. So that means DC is a low frequency signal, very low frequency signal. So in that case, they pass the DC totally. But this is only intuitive understanding. But if you have learned something about Fourier transform, for example, and then we can derive the transfer function easily, right? So in that case, first we assume like the output Laplace transform is like this, is U0s. So what's this one? Because this one we can consider this is a voltage divider, right? Voltage divider. So in that case, what's the resistance for this one? First is R, right? R is resistance. So for the C, for the capacitor, what's the resistance we can write? Actually, it's a 1 over SC. Do you remember? So the S is the Laplace symbol. So in that case, this one you can treat this one as a resistor. So you can treat the resistance of a capacitor is 1 over SC, 1 over SC. In that case, according to the voltage divider, so the output of the capacitor is here should be, you just treat this one as a resistance. So it's 1 over SC, right? So this is a output, but we need to times the U input S. So in that case, the transfer function is, for this one, the transfer function is U OS over UIS, right? And then it is equals to we times SC together, and then we can have 1 times S and RC plus 1. So you can see this is a standard first order system, right? And the statistic gain here K is 1. So in that case, because this is a passive filter, right? It's a passive filter. So the gain is 1. And you can change R and C, you can change the cutoff frequency. You know, first order system. So this one is can be written standard format is. So the T is equals to RC is a time constant. And then you can draw the body plot for this one. And So the body plot for this one is because first order. So you can get like something like this. So similarly, you can derive the transfer function for the high pass filter as well. So this is only for one first order, because you only use one capacitor, right? If you want to derive high order, so you need to cascade several RC network. But this design will make it very difficult because of coupling. So the design here, you remember I derived this one, right? Transfer function is HS 1 over RC. You can see 1 over RCS plus 1. So this is the first order, right? So actually it's a similar here. So this and then you draw the amplitude, magnitude response. You use this formula because you assume this one S is j omega, right? And S is j omega, and then this is a complex number, right? And then you can calculate the magnitude. How to calculate magnitude? It's like the one doesn't change, but in the denominator, is a square of a complex part, an imaginary part, and a real part. That means this real part square, one square is still one. And this is if S equal j omega, right? It's here, j omega. And then your imaginary part is RC omega. So RC omega square, right? So you can see if when omega change, because omega is the input frequency, the signal frequency. When the omega change increase, and then the overall the gain will decrease or increase. Will decrease, right? Will omega increase, the overall the gain will decrease. So that means that when omega is 0, this is 1. So this is a pass, right? But when omega is greater than 0, this one will be less than 1. And when omega very big, can be 0, right? Omega very big, this one can be very small, extremely small, right? So this is a low pass. On the other hand, so this is low pass, and you can design high order filter for like this, right? Cascaded. But this is not good because when you design, very difficult to select C1, C2, R1, R2 because they are coupled, right? So this is give you how to design the low pass filter, but this is passive filter. This is fundamental. Just tell you the idea why you can just use RC circuit to implement filtering. So think about it. This looks straightforward, but it's amazing. Like they can use just simple RC circuit can build a filter. So you can even build a high order filter, passive high order filter. But from design point of view, they are quite complex. And another one is active filter. So active filter, they have advantage. So it has several advantage. So this will give you a very simple example. So what's you look at the amplifier circuit. So this one is inverting amplifier circuit, right? If you treat this one, because as I said, C capacitor can treat it as a resistance as well. So you can treat this one as 1 over SC2, right? 1 over SC2. And then this together, they treat it as a resistor to get resistance. And you can get resistance. And then you can get this is called the inverting amplifier, right? So what's the output? So what output is the way out? Is like you just, if you treat this one as a resistor together, and then you just minus this resistance value divided by the R1, right? You can get the gain. So, but this one, because you have memory element, and then you can design a filter. So this is a low pass filter. You can design a low pass filter with transfer function like this, right? Transfer function like this. So you can select the value C and R. You can you can design the cutoff frequency. For the high pass, it's the same. You can design the same thing, right? And another kind of class is like they have Butterworth filter, Chebyshev filter, and other filter like elliptic filter as well. So their name is based on the magnitude response. So some like a very flat. This is a Butterworth filter. Butterworth filter is the most flat filter. So in the passband, they are very flat. So normally we use Butterworth filter for the anti-aliasing purpose. So, but the disadvantage is the roll-off is not sharp. So you can see the first order is very flat. But you can select other filter. For example, Chebyshev filter, they have ripple. Even in the passband, they have some ripple. They are not very flat, but they are very sharp. They go to the same order, but they are sharp. The sharpest filter is the Chebyshev filter. So this is the magnitude response for the Butterworth filter. So looks like this is quite complex, but if you use computer help you, this is very easy. So this is I derived the transfer function for the. This is a second order. You can see second order. Here you can change this y1, y2, y3, y4. They are called admittance. So you can change it to different value, and then this k is the amplifier. This is a actually is a non-inverting amplifier. You can change the RA and RB, change the gain, and this is a k you can design. You design this k by using this amplifier we discussed last week. And also you can select Y1, Y2 for different value. For example, Y1 you use a resistor, right? Y1 because this is called admittance. So this is a 1 over of resistance. So if you put R1, Y1 is R, Y2 is a Y2. Normally the Y2 is a capacitor. Y4 is a capacitor. Y3 is a resistor. So you select this kind of structure is called a silent K structure. Silent K structure plus again amplifier. You can construct a second order filter, right? So I already write the transfer function for you already. So if you select like this, your transfer function you can directly use this one. So this is a standard silent key structure. Silent key structure. So because time is too quick, and I will show you use MATLAB to design this filter. Because if you use hand to design, I think it's even you have this transfer function. You can even design because I ask you maybe design fourth order or sixth order, and then you can design separately maybe 3 second order, and then merge them together. You can get a sixth order filter. But even that, you need to select R1, R2, and C1, C2 to satisfy your frequency response requirement. So fortunately, we can use MATLAB. I show you use MATLAB. So for example, I go to I show you how to use MATLAB to design this. So basically, you can download this one. This is free. So this software is free. Of course, you have other choice, but this one I think use as a starting point. You just search AFD and MATLAB. So you can download this so this is analog filter design. So you can download, but you need to register, and then you can download. This free, and this one very easy to use. You just like put there and put it to a folder like me, and then you can just type AFD. You type AFD, and then it will appear this window. For example, you want to design low pass, right? Low pass, you can design other high pass. If band pass, you can combine with low pass and high pass. And also you can select different filter. We normally use Butterworth. So you have Bessel and Chebyshev and elliptic. So you can select order as well. You can select a different order. For example, you want to fourth order. So you can have a cutoff frequency as well. For example, 10 Hertz or maybe 100 Hertz. And then after this, you can build the circuit. So that circuit they give to you. So this is the circuit, and then you can select a different value. For example, here I talked to you before, right? Here you can see R1 is too big. It's 1.7 micro ohm. So it's too big, right? And but we capacitor is small. It's nano farad. So you can increase this one, for example, to 10, and then so this one will reduce to 172 kilo ohm. So this one is acceptable. And then you design this filter. You can put into multi-sim, right? But here you can also, this silent key structure, you can use other structure. So they have other structure as well. They are all implement the low pass filter, but the most commonly used is silent key. So you can put, for example, 1 micro one, and then the R1 will become smaller. Yeah. So this stage 1. You also have stage 2. You can go to stage 2 because you have fourth order, right? So you need to at least a 2 stage. So 1 stage is 2 order. You need another stage. So stage 2, you can see you can adjust again. For example, you have 10. So this is the value, right? This one you designed, right? And then you can also analyze. For example, you have some resistor tolerance. Of course, you can use multi-sim to do the simulation. Multi-sim is more real than the MATLAB. So you can, but when you design, you maybe can use like a test like this. Pass band polarize. You want to non-inverting or inverting, depends on you. So and then you can also have stage details. So you can analyze. So you can see for each stage what's the Q factor, and the Q factor in the future I will discuss with you. And also they have a pass band and the stop band and all the information. You can for different stage you can have different analysis. So you can also different stage you can see have different step response. No, sorry, frequency response. So that's why I show you this one how to design. After you design, you can use either MATLAB. For example, I open the MATLAB one. So I have tested the total fourth order things, and then I can simulate the. After I input the parameters I designed here, actually the computer design, and I can analyze. Maybe I close this one. Close this one. So that's the overall design. This one is of two stage at fourth order, right? This you can see from here you can analyze what's my cutoff frequency. Actually, it's 10 hertz, right? So if minus 3 dB should be 10 hertz. A little because I have put some tolerant. So this one is not exactly 10 hertz. So you can see this is I designed the passband. This is the phase response. So I have each stage. So this stage 2, this stage 1 frequency response. So you can use MATLAB to implement for you, right? So if necessary, I can publish this in the website, or you do MATLAB analysis of your design. And but the most important thing, because you need to implement in the multi-sim. So multi-sim is here. If I open one, I think I have a filter as well. So they have a low pass filter. Maybe because the time is limited, maybe I leave this one to Jeffy. Jeffy, because Jeffy is very familiar with the multi-sim. So I hope you can learn from Jeffy. Jeffy,
Yeah, I'm here, sir.
yeah. Do you want to give some very quick explanation about multi-sim? You can either use filter design or use instrumentation amplifier design. And yeah. And so how about what's maybe student can give feedback? Do you think like we maybe spend some time here? You think it's
Yeah.
necessary?
Yeah, I can. What I'll do is I'll show the basic examples, and I'll go to every room and ask them if they have any doubts. I can do
Okay. Yeah. So in that case, I make you as a co-host. It's a host,
that.
right?
Sure. Co-host is enough.
Yeah. Make you host. I think make you host.
Yeah.
And yeah. After that, we will go to a breakout room to discuss.
Yeah.
Yeah. Okay. So
Yeah.
your turn.
Yeah. Sure. So, are you able to see my screen?